All right, so anyway, this, you don't need to write this down. I mean, you can, but I'm gonna quickly scroll through this. But on our website, under today's homework, that's tomorrow's, under today's homework on Thursday. Now, has everybody been to the website at one point in time? Okay. On Google Classroom, I think the link is still there. Hopefully you bookmarked it, whatever. But if you go to the class website, under Thursday, I've got quiz 2.4 through 2.7 notes. Okay. Now, they're just kind of summary, just kind of the things that are on the quiz. It doesn't work out anything or anything. But it's just kind of going over what it's about. So since we've kind of covered, at least introduced all of the different things that are in these sections, we can kind of talk about them here. So I would say half the quiz, half the points are probably chart, global, max, min, kinds of stuff. That there's a lot of points in each one of those kind of problems. Those are important. Those are really important ideas that we have here. Maybe another third of the points is from the differential equations stuff, verifying that it's a solution and solving maybe some simple ones, which of course involves antiderivative. And then just kind of knowing those derivative rules and being able to do some derivatives, which of course you have to do inside of those problems also, would be the remaining few points. I don't know what's that leave, 1/6, I guess would be. I mean, I just kind of guessing at those fractions. I haven't even made up the quiz completely, but that's my intent there, is kind of that, to break it out with those things, okay? So our derivative rules, of course, we talked about. If you're adding functions together, you can just do their individual derivatives. If you have a constant out front, and again, all of this is on that in those notes up on the website. So if you have a constant out front, it just hangs out there. If you have a constant multiplied by the x on the inside, you kick it out and leave it in. If you have the power, it's just our power rule. If you have e to the x, it's this. If you have something else to the x, I used b here the other day, I used a, but b to the x, like 2 to the x, you'd have 2 to the x ln 2. 3 to the x, you'd have 3 to the x ln 3. And Max, one of the things we're going to talk about, and you probably saw that in that video, is, people confuse these two here, right? The power, right? Power, when it's x to a number, you bring the number down. When it's a number raised to an x, and it's this rule here, okay? It's a different rule. And then log, natural log, it's 1 over x. But if it's a different base, it's still 1 over x, but then you have to tack on this here. So we have those derivative rules, and then we had sine and cosine. I think we also talked about tangent, but that's not going to be on there. The tangent one's not going to be on there, so you have to worry about that. But derivative sine is cosine, derivative cosine is negative sine. So, and then, of course, our chart, we talked about the chart stuff. That's when we do these number lines. We do the derivative, set it equal to 0. We put those numbers on there. Then we check numbers in between. We plug them into f prime to see if we have positive or negative. So, and Max, the whole reason for that was, and if you watched that first video, you would have seen that, I guess. But the idea there being, if back in chapter 1, if I told you you had an f prime graph like this, what would you do? Well, you'd say, hey, that's negative, positive, negative, positive. That tells you that f is decreasing, increasing, decreasing, increasing, right? When we were doing the matching stuff. So if we knew this information about f prime, it really told us what was going on with f. We knew we had a local min here, local max here, local min here. Well, so we do the same thing with equations. We do the derivative set equal to 0, so we know where it crosses the x-axis. We check in between. This gives us that same information that a graph would give us, okay? So we can tell that this is increasing, decreasing, increasing, decreasing. You want inflection points, you do the second derivative. This would tell you the graph's concave down, concave up, concave down, concave down, concave up, concave down, okay? Now, if we're doing a global max min, of course, we have to check the endpoints and we have to check where the derivative is 0. So we find those points, and then we got to plug those back into the original to see which one has the biggest y value. So this point, this point, this point, this point, and this point. And we plug them back to the original, see what the y values are. The biggest one would be our max, and the littlest one down here, that'd be our min. Okay, so that's global max min. So that's the stuff that's about half the quiz, is being able to go through and do this stuff. Okay, differential equations. Yesterday we said it's an equation that contains derivatives. So something like this would be an example. The solution to a differential equation derivative function. So Max, this is brand new stuff. A little bit of a side trip, but it involves derivatives. So think of that like quadratic equations. Quadratic equations are equations that have what in them? An x squared, right? Linear equations are equations that have an x to the first in them. Cubic equations are equations that have an x cubed in them. Trig equations are equations that have a trig function in it, right? A differential equation is an equation that has a derivative in it. It's got a y prime or a y double prime or both, right? That's a differential equation. Now, the real weird kind of strange thing is quadratic, cubic, trig equations. They have number answers, whereas a differential equation, the answer to a differential equation is the original function. So in this case, the differential equation is this. The solution to that differential equation is this, okay, which we get by the antiderivative, right? We just do the, oh, that's another term we've thrown in here. I think we did that. I think the antiderivative just means going reverse, right? Going from y prime to y. So we just kind of use the derivative rules in reverse to get that, okay? So that's the solution to the differential equation right there. And we can check it by just doing the derivative and seeing, yep, we get 6x plus 5, okay? 3 types of differential equations we said. There's the type that we can just easily solve by doing an antiderivative like the one I just showed you. There's this one that we don't know how to solve because it's got a y in it instead of just x's, so that's a problem. So you see a y in it. We can't just do an antiderivative on that now. So we're just going to memorize this as a solution. What was that, number 47? I think number 47 on one of the homeworks was that problem. You needed to recognize that number 47 was this differential equation. So it's that solution. We just write it down and use it. And we'll look at that problem. Okay? So there's that one. And then there's a whole bunch you had on homework, number 6, number 17, number 19, number 20. They were just weird differential equations that look like this. And we just, or like this, and we just can check a solution. If they tell us something's a solution, we can check it and see by plugging in. Like if I told you that 8 was a solution to a quadratic equation, you can just plug the 8 in and see if it works, okay? Even though you might not know how to solve it, okay? If I gave you a 5th degree equation, you guys wouldn't know how to solve it. There's no fancy formula for like the quadratic formula to do a 5th degree equation. But I can tell you this, I could ask you, does 2 work? You put a 2 in and you can tell, okay? And that's it. I mean, that's your differential equation stuff. That's your chart stuff. That's your derivative rules. That's the stuff that's going to be on our quiz up there, okay? All right. So if we go through our homework today, like we have right here, so here's number 6. So we're not going to go through every single, you know, and these are easy points that I can get. Might help your grade here. We'll give you a little credit for doing something. Okay, what else? That's all there. 47. What's 47? And then, yeah. Okay. Just got to get up earlier so we can get farther on the goal. Okay. That's good. Okay. Yeah, we got it. Yeah. Okay. Right. Well, you'll have to, we kind of went off that a little bit. You have to go on the website. What's that? Let's see. All right, now, So the this was yesterday's. Go and jot that down. Then the other ones just have to go on the website because I kind of changed that with the assignment sheet. I mean, it'll be in the video. It'll say the video too, but it's also on the website. You can just go under each day's. Okay. All right. So the idea here is on these difference equations, show that this is a solution. So I'm just going to pick out a few, and then hopefully that's enough here. If you've got any other questions, see me individually. But so they give you this differential equation. They say verify that this is a solution, right? So what did we say before? We said difference equation with a derivative in it. The original function y is the solution. So is this a solution? So we got to plug this into here. So right there's a y. We're going to plug that in for the y. Right here's a y prime. So we're going to do the derivative of this, and we're going to plug that over there, right? So I've got to do the derivative of that y. So I'm going to do that. Now here's where people usually screw up on this one. You bring the 1/2 down in front. We always leave the inside alone. We drop that to a -1/2, but then aren't we multiplying right there by -1? When you're multiplying the x by something, you have to kick that out. So we have to kick out a -1. And then I'll just rearrange this a little bit. This negative power is going to flip down to the bottom because I'm going to plug it in and try to match and see that they're equal. So I'm going to take this and I'm going to flip that down to the bottom with that 2. So that goes down there like that. The -1 I can just leave on top. So now that I'm going to put right over here like that. Right? And then this one, now I'm going to take my y, I'm going to take that, and I'm going to put it right there. So I have -1/2 times that. Oh, look, they're the same. So check, yes, it is a solution. Yes, it is, or verify, just said show that it is, so I just did. Okay? And so these next ones are all very much the same. Oh, then on also part of 6, they said show that it's got, did somebody ask this? No, that might have been the other class. Somebody asked if there was more than one solution in the other class to a difference equation. Could be, right here, they just showed you. It says show that this one is too. Okay? Because same thing. If I do the derivative of this, bring the 1/2 down in front, drop that to negative, kick out a -1. See, so I'm guessing, like Jesse on CDJ, if you didn't kick out that -1, you probably said it wasn't a solution, right? Because they wouldn't have matched, right? Yeah, if you don't kick out that -1, then they don't match. Well, you kick out -1 on this one, the negative cancels that negative, so you just get positive, right? Same thing. So you take that, you put it over there for that's y prime, I just did, so you put it right there for y prime. Then I'm going to take this and put it right there for that y. But then what happens, this negative I have down here and the negative I have up here cancel, and then they become positive. So they do matching. Okay? So that was a little harder one. Once you got to like 17 here, then it got easier, actually. 17 is really easy compared to that. I mean, here's the differential equation. Here's the solution. So wherever I see a y, I'm going to put this x cubed. So I put an x cubed there. Y prime, I'm going to put a 3x squared, right? So I just put the y prime in there. That's just times, right? That's just times right there. So I put an x cubed right there. I get 3x cubed. X times 3x squared is 3x cubed. No. There you know what I mean? So that was actually a lot easier than 6 because it was just an easy function to work with. Okay? 19. Now, on 19, they give it to you like this. Now, I want to make a couple comments about this. Number one, they wrote y of t. Well, I don't care about that. That's the same as y. That doesn't matter, right? I mean, it doesn't matter. They wrote y of t. That's just y, okay? And then I don't like t squared over 2. I would rather write that as what? 1/2 t squared. That's much better to do the derivative with, especially when we get to chapter 3 and we learn about the quotient rule. And a lot of you are going to look at that as a quotient. You're going to try to do the quotient rule, which is silly. It just gets complicated. You don't want to do that. You just want to think of that as 1/2 t squared. So now, oh, and by the way, I did this. I wrote this one backwards on, or not backwards, but on all these other ones, I was putting the differential equation first over here and the solution over here. It doesn't matter. I swear to God, I've had people that memorize, oh, the one on the left is where I put the t. No. Where do you put the t? Why do we even put the t? Which one do we put the t in? The differential equation, the one that's got y prime, because we're taking the solution and plugging it in to see if it's equal. So I purposely at 19 switched it around. Right? So you're not just memorizing, you gotta know what you're trying to do. This is our solution right here. We want to take that and plug it in, just like in algebra class. If I tell you 8's the solution, you take 8 and you plug it in. So we want to take 1/2 t squared and plug it in. Now there's no y anywhere, so there's nowhere to plug 1/2 t squared, but there is a y prime, so we got to do y prime. Well, what's the derivative of 1/2 t squared? Bring the 2 down, cancels that, you just get t, so y prime is t. So in place of y prime, you put a t. There's nothing to plug in over here, it's just t. Oh, they match. Okay? So sometimes those simple ones are almost confusing because you're not sure what to do. Then on 20 was different. I don't think I have 20 over here. But on 20, they said y prime equals y, right? Well, on that one, you put t in here for y prime, and for y, you put 1/2 t squared. Oh, those aren't the same. So then that's enough. Right? That's enough. And then 25 was the same thing. Right? So you plug that in and you see if you get a match. Okay. So that's the differential equation section. So we're gonna do a little more with that, with the differential equations here today. But matter of fact, let's talk about a couple things in this section. So if you turn in your books to page 128, if you're not there already. 128. And so one of the things I want you to be able to do is be able to translate the language into equations. Okay? So for example, they say y prime equals 0. Well, in English, that would be like saying the growth rate of y is 0. The rate of change of y is 0. Of course, that would mean y would be constant, right? If the rate of change is 0, if there's no change, then you know y would just be some constant, right? C, right? If you're doing an antiderivative of 0, it's a constant, right? And they give an example. Y is the position of a fixed object, like something that doesn't move, something that's not, the car's not moving, the y prime would be 0. Or it could be the value of a no-interest bank deposit. If you put some money in a coffee can and bury it in your backyard, right, the rate of growth would be 0, right? Actually, because of inflation, it would actually be negative because it would lose value. But anyway, so how about the next one? Y prime equals 0.06 y. Well, that's saying that the rate of growth is proportional to the amount that's there. And this, of course, is the compound interest one. This is the y equals AE to the KT, right? The rate of growth, if it's your money, the rate of growth is proportional to the amount you have. And that's an example. You get the value of a bank deposit at 6% interest, compounded continuously. So the rate of growth is proportional to, by some proportionality constant, the amount there. So if you hear that in any of these problems, word proportional, what that means is stick in a K. Y prime equals KY. If it says the rate of growth of Y is proportional to the value of Y, you hear that proportional, you stick in a K. Here, the rate of growth is proportional to the time. Okay? Well, that would be like that example. We're going to do this here in a second. If I just drop a ball, we talked about that gravity, right? If I just drop a ball, the rate of change of its height is proportional to the time because it's increasing because of the pull of gravity, right? So its rate, its velocity, which is what y prime would be, is going to be getting greater the time goes, okay? Because it's speeding up because of the pull of gravity. Okay, y double prime equals k. That would be constant acceleration. Well, again, that's the one we talked about. We're going to talk about that here in a minute. And here's a good one. This is actually the other differential equation we're going to memorize. Now, we're not going to do it right now, but this would be This has actually got a name. This is Newton's law of cooling is what this is. If you think about Y being the temperature of my coffee right here, okay, in my fancy little, this is the Ozark Trail. Make sure you get this on video. This is the Walmart range. Anybody got one of these? Anybody got the real thing, the Yeti? Arctic is the other. It's spelled like RTIC or something. Arctic. There's Ozark Trail from Walmart. There's Arctic and there's Yeti. And the Yeti's like way more expensive. You have a Yeti?
Yeah.
But the Arctic's just as good.
Yeah.
Yeah. Do you have a great big one?
Yeah.
Is yours like this?
My dad, yeah. A couple of those.
Because my daughter, I had to buy her one there because everybody's
She was
got one.
asking us
Yeah,
what she should get.
which size? I know, because everybody's got one. She had that, so I had to buy it. But I can tell you, I said, I'm not buying it yet. I'll buy you the cheap Walmart one, whatever. Anyway, okay, I digress. So, let's say Y is the temperature of the coffee, okay? So, Y prime would be what?
How is it cool?
The rate of change, right? How fast? So, what would be the units on Y prime? Degree, no, not degrees. The temperature, the units on Y would be degrees. Degrees per second or degrees per minute, maybe let's say degrees per minute, right? Be how fast the coffee's cooling, right? So what this would say is the rate the coffee's cooling is proportional to, so if I was going to give you a sentence and wanted you to write this out, which I may do on the quiz, if I gave you a sentence and wanted you to write the differential equation, okay, it would sound like this. The rate the coffee's cooling, of course, as soon as you hear the rate, you know that's the prime, right? So the rate is proportional to, so you hear that, you put a K, right, for constant. The difference of the temperature of the coffee and, what do you suppose the 65 is? Room temperature. Because think about it. When does the coffee cool the fastest? Well, the lower this is, right? If your room temperature is colder, it's going to cool faster. But this is constant. It's not going to change, right? So let's say we're in a 65-degree room. So I bring my coffee in here. I pour my coffee and I come in. When is it cooling the fastest? When the coffee is at hottest, right? Because it cools pretty fast. Now, as the coffee gets down towards room temperature, it's not cooling as fast anymore, is it? I mean, in degrees per minute, right? Because it doesn't have as many. So if you got 150 degree coffee in a 65-degree room, right, it's going to be cooling pretty fast. But as it gets down towards room temperature, it's going to kind of level off, right? So actually what this is just an exponential curve shifted up to room temperature. It's going to come down and level off like this. But now think about it. When is this number here going to be the biggest in the parentheses? When Y is the highest, right? And that's the temperature of the coffee, right? So the bigger this number is, the bigger this will be, right? That's the idea, okay? And of course, this is the rate of change. So the coffee is going to cool at a rate that is proportional to the difference between the temperature of the coffee and the room temperature, okay? So the bigger that is, okay, will will K be positive or negative in this scenario? Why? Think about this. K's got to be negative, right? What would this be here? Positive or negative in the parentheses? Why? Because the coffee's hotter than room temperature. Let's assume, right? So this is bigger than this. This has to be positive. What's Y prime? No, it's not decreasing. Careful what you're saying. What's decreasing? Which is what variable up here? Y. Y is decreasing. Think of the chart. Y is decreasing. So what's Y prime got to be? Y prime's got to be negative. Y prime's got to be negative. We know this is positive, so the only way these two sides are equal is if K is negative. But it would be wrong to say K is negative because the coffee's decreasing. K's not negative because the coffee's decreasing.
What's negative because the coffee's decreasing? Y prime is negative because the coffee's decreasing. So it'd be wrong to say K is negative because the coffee's decreasing. Because what if I flip these two around? What if I made this 65 minus Y? Now what's K going to be? K is going to be positive because 65 minus Y is going to be negative, right? We know Y prime has to be negative here because Y is decreasing. So if I flip this around and made this negative, then the K would have to be positive, right? So the two sides would be negative. Okay, so things like that I want you to be able to understand in a situation. I want to be able to talk about, because that's the value of differential equations, is you can talk about the rate of change of an object, and then you can translate that into a math sentence easily. Of course, that's why you take a class then in differential equations, is in solving this, because the problem with this differential equation is you can't, if I said, hey, after 10 minutes, how hot's the coffee? There's nowhere to plug a 10. Right? You need the solution to this differential equation so you can then use it and find some values and so forth. So that's a key thing about differential equations. Okay, one last thing, you might want to jot this down in your notes, and then we're going to move on to the other problems. We got to do some stuff with we need the hats today, so let's get those out. Pass those around while you're jotting this down. Okay? And I'll take a drink of mine. Still hot coffee. These things really do work. It's amazing.
Does yours have like a notch on the lid when you can close it?
Like to close that up? No. Does yours?
The like Arctic ones do. The
The
Yetis
Arctic ones
don't
do?
know.
The
Maybe
Yetis
you
do?
can buy special lids.
What? And it seems amazing to me that with that hole to drink out of, the heat doesn't escape like crazy. I mean, I would think it would. So that's what is kind of, so I'm guessing with the lid, you would think it, but I was going to buy the Yeti, and then my son told me he saw some YouTube video that showed the Ozark Trail one was just good.
Yeah.
So I looked it up, and yeah, they were running these tests on it. Who knows, they could be doctor, but I think it works fine. So, I mean, I think at Walmart this was like $7, and I think the Yeti was 30 or 40. Yeah, crazy. Probably made in the same factory. You know what I mean? Yeah, in the same factory.
Well, like, have you seen how expensive like their coolers are?
Oh yeah. That's when I first heard about Yeti. I saw them at Builders or something. I saw this cooler like $300 for this cooler.
These coolers are crazy.
Well, they must be
Well, they work,
amazing.
yeah.
I think
They
they work.
keep ice on for like 7 to 14 days.
Is that yeah? I mean that's cool. All right.
What would you guys?
Yeah, well,
It's like people buying real money as it, but
Yeah,
value
like
ice in it.
fishermen.
yeah. I mean, if you're going to be out somewhere in the wilderness for a weekend or whatever. Okay, so initial value problem. So don't get freaked out by it. All it means is you have a differential equation, and then they give you an initial condition. Because remember, when we solve a differential equation, we can't solve a lot of them, but when we do, if we do an antiderivative, we always get that plus C, right? We get that plus C on there. So like we said, the vertical shift, we don't know where the original graph is for sure. Well, if you give an initial condition, you give a starting point for that, then it is, I don't think you'll be able to log in here. Start class, there you go. I should be able to log in. All right. Anyway, back to this. So so initial value problem is just a difference equation. So if it says solve the initial value problem, so if you get a homework problem, it says solve the initial value problem, it just means solve the differential equation, right? Do the antiderivative, which is probably what you're doing, right? But then you can plug in, we'll do an example, then you can plug in the initial condition. So you get your plus C, you can plug in your initial condition, and you can find your C value. That's all that means. Okay. All right. So one last example of initial condition. You can put this in your notes or not. It doesn't really matter at this point. But so remember we talked about position, velocity, acceleration, right? So if I got height, velocity, acceleration, right? So velocity, that would be the same thing as h prime, right? And acceleration would be the same thing as v prime, but it would also be the same as h double prime, right? So acceleration could be called v prime, but it could also be called h double prime, right? As I go down here, this would be, say, meters. Well, it's going to be feet. This could be feet. This could be feet per second. And this could be feet per second squared, right? So we already talked about this example. And we've already talked about this scenario where acceleration of gravity is negative 32 feet per second squared, right? Now, back in chapter 1, I gave you the height and the velocity equations of a ball in free fall. Well, now we could actually build those equations. So I just want to go through and do that for you. You won't have to do this, but I just want to show you this. But this is an example of an initial condition, okay, with an initial condition. So I know that my acceleration, now I don't have to write a of t, I can just write that as a, is negative 32. But we also know that a is the same as h double prime. So I'm going to write that h double prime equals negative 32. Now, I want to write h prime. I want to do the antiderivative of that. I want to solve this differential equation. Now, to solve it, I actually have to go to h, right, the original function. So I'm going to have to do the antiderivative twice, okay? So what's the antiderivative of negative 32? Negative 32, we're going to use t instead of x, but you're right, plus some c. Now, what is that c? Well, I don't know. I don't have initial condition, but at time 0, what would be my velocity? When t equals 0, I'm going to call my initial velocity, I'm going to just call that v sub 0, right? So when t's a 0, this would disappear, right? Everybody with me? When t's a 0, this would go away. So c, isn't this just my initial velocity right here? Right? Because h prime is my velocity. So I'm going to replace that c with a v sub 0. And if you remember, wasn't that our velocity equation of a ball? That was it. That was the equation. Negative 32t plus v sub 0. I think we wrote v sub 0 minus 32t. I think is how we wrote it back in chapter 1. I think we wrote it like this. But same thing. Now let's do the antiderivative again. Now we would get h. Now what's the antiderivative of negative 32t? Negative 16t squared, right? You raise that up to 2, divide by 2. Plus, remember, v sub 0 is just a number. So what's the antiderivative of just a number? In this case, t, though, right? So the antiderivative of 7 is just 7x, so 7t. And then plus some c, right? Now, what is that c? Well, again, at time 0, this would disappear and this would disappear. So c would just be my height at time 0, which we could call our initial height. So I'm going to erase that c and I'm going to just call that h sub 0. Okay? And wasn't that our equation, if you remember, for the height? I think again we wrote it a little different order, but it was the same thing. So those equations aren't just magic. Those we can actually build those from the fact we know the acceleration or the second derivative is negative 32, and then we just build them from there. Okay, so I just wanted to show you that. Essentially, those by solving the differential equation, we come up with those equations. Okay, all right. So enough of that. Let's move on to section 6, and this is problem 37 on there. I wanted to make mention of this. It talked about average velocity and then it talked about instantaneous velocity. Okay, so this was a position function, so this was meters. So this would be in meters, it said. So your velocity would be x prime, right? Now that'd be your instantaneous velocity. So I've said this multiple times, but average rate of change, and I can't say it often enough, when we hear average rate of change, we think slope between 2 points. Slope between 2 points. So what I want to do is, and the 2 points they wanted you to use are 1 and e. So this is going to be x of e minus x of 1. Now it seems weird to be using x as a function, but that's what it is, right? We're talking about a particle moving on the x-axis, so a lot of times we do that. So we're not using p as our position function or h, or we're using x, right? Because it's on the x-axis, it said.
So we're just gonna do that over E minus 1. You've got to understand, average rate of change means slope between 2 points. So they give you the 2 points. All you have to do is plug them in. So this would be meters up here. This would be seconds down here. So that's going to be meters per second. Okay, well, what's ln of E? 1. What's ln of 1? 0 over E minus 1. So that's just 1 over E minus 1. So that's your answer. That'd be meters per second. Okay, for 37A. For B, the instantaneous velocity, now we need the derivative. Well, what's the derivative of ln t? 1 over t. 1 over t. And they want it when t is equal to e. So we plug in an e, so that's x prime at e, and that would be 1 over e. And that would be meters per second. Okay? So there's your answers to 37. Okay? It's not a tough concept, but it's really pretty easy when you look at it. So that was easy. But you got to understand the terminology. What's it saying? Average rate of change means slope between 2 points. Okay, they gave you the 2 points. It's meters over seconds, right? And then, of course, derivative is meters per second. So we do the derivative, we get that. All right. What do I have next up here? Oh, yeah, 47. So this is that bank one. First National Bank has 8% interest compounded continuously. Okay, well, that is this differential equation. So, and some people, when you guys were here earlier, Will's question was exactly right to me. He said, is this the one where we had to memorize? And if you remember, that's exactly correct. So when we were over here, we talked about types of differential equations. Right here, there's differential equations we don't know how to solve because it's got that y, and in this case it's a p. We're just going to memorize that solution. Is this? Okay, so that's the only one. That right now, that's the one we have. It's compound interest. And so I have to notice that that's like my y, that's my k, and that's my other, this is y prime, that's y. So this would be p equals a e to the 0.08 t, because that's my k, and that's the k right there. So you've just got to be able to, from this, just write that down. It's just a memorize thing. So any problem that looks like this, if it's compound interest, right, it's going to have this look. Now, if $2,000 is deposited now, how much will it be worth in 10 years? So then Will's next question to me is the 2,000 just the A? Well, yes, but I'd rather you think of it this way. Because I might ask it in a different way. I might say, what if the 2,000 is, how much is there in year 2? How much is there in year 5? Well, then the 2,000 wouldn't be the A, right? Because here's why. Because when I put a 0 in, what 2,000 now means times 0. So the 2,000 is really the P. And then when I put the 0 in here, well, what's e to the 0? 1. And then that's 2,000. So yes, the A is the 2,000, but only if you're talking about year 0. Okay, so now I've got this equation right here. Now all you have to do is put a 10 in for t and type in your calculator. That's it. So it's a really easy problem. Now that example I gave you, if I said, what if it was year 2? What if it was year 2? And then I wanted to know year 10. So what if year 2 was 2,000? Well, then you'd have 2,000 equals A e to the 0.08 times 2. Let's do that on the calculator. Let's get it. That. Okay, go onto your calculator screen, just on the calculator screen, and let's just solve that real quick. Okay, so take 2,000 divided by, and then just do e raised to the 0.08 times 2. Okay, hit enter. Okay, so there would be your A value. All right, now, so A would be that. So now my equation is whatever that number was, e to the 0.08. Now let's put a 10 in there. Okay, so Zach, do that. So take that number right up there that you just had, okay, times e to the 0.08 times 10. Okay, and you'd have that much. Okay, do you see the difference there? Now, some people would say this, okay, but all that means is you did it over an 8-year period, right? So couldn't I just, so even in that case, I could let the 2,000 be the A, but remember, that's at time 0. So if I'm going to go from year 2 to 10, is that the same as year 0 to 8? It is. So you could have let that be a 2,000, and then instead of a 10 here, put an 8. And so Zach, go ahead and do that. So do 2,000 times e to the 0.08 times 8. And this is going to be embarrassing if we don't get the same number. Right? So you see how it's the same thing. So again, back to your question is, so if we deposit 2,000, is that the A value? Well, it's the A value at time 0, right? The P is your value always. The P is the value always. But at time 0, P and A will be the same. Okay, because this will be just e to the 0, which is 1. So P and A will be the same. Okay, so you can do it either way. Do it either way. I know I've done a problem in the past where I say, you put some money in when you graduate high school, you're 18, how much will you have when you're 65? You know, well, you can do it from 18 to 65, or you can just say, hey, that's a period of 47 years, you know, and do it from 0 to 47, right? It'd be the same amount. It's the same idea. So either way, if you run into one of those problems. Okay, let's go to the trig problem now. The third, well, I don't want to spend a lot of time on this because we did a lot of this yesterday. This is a no calculator one. I want to spend the rest of our time mostly doing the calculator problem and then trying to give you at least a little bit of work time here today. So we've talked about some derivative rules a little bit. We've talked about differential equations quite a bit because that's our newest thing. And now we want to talk about our max min, our chart stuff, whatever. We've already spent a lot of time talking about that, but so here was our original function on 37. We started this in class yesterday. We want to find the max min, all that stuff. And so we did the derivative. We set it equal to 0. So we solve it. So max, of course, we were talking about how we have to know our trig values here. So cosine is negative over in these two quadrants here, -1/2. Well, that would be up here at 2 pi thirds. And then that would be down here at 4 pi thirds. Okay. Now, we did a number line, and what did our number line end up looking like on that yesterday? Wasn't it all positive? It didn't end up being this yesterday. Did we do that much? Didn't we do that part of it?
I got positive, negative, positive.
Yeah, that's what
We did?
Yeah, because it's -1.
Oh, yeah. Oh, you're right. Okay, never mind. Okay, so, oh, yeah. No, that's true. Yeah, because it goes up, then down. Yeah, that's right. So we put in, yes, because we put in, that's right, we put in 0, we put in pi, we put in 2 pi. And then, Max, what we've talked about is we put those back into f prime right here. So that's that thing we were talking about, right? So you put a 0 into here, you get a positive number. You put a pi in, you get a negative number. You put 2 pi in, you get a positive number. So that's our f, and we want to label that's f prime. So f is going to go up, then down, then up. But the question then becomes, so if they want to know the local max, of course, that's in here. If they want to know the local min, that's in here. They want to know where it's increasing, decreasing, that's all in there. If we want to do the inflection points, we do the second derivative, right, and go from there. But we'll get to that in our calculator problem here in a little bit. But if we had to do a list of candidates, and I think I started it, I think I did this one. Didn't we do this one in class? Did we get that far? On list of candidates, or did we? I don't think we did. Okay. So here's your original. So here's where it can get a little tricky when you don't have a calculator, if you can't use a calculator. Like plugging in a 0 is easy. 1/2 times 0, 0, sine of 0, 0. So that's easy.
You plug in a 2 pi, 1/2 times 2 pi is just pi. And then sine of 2 pi is 0, so that's just pi. Okay, so that's easy even without a calculator. Then it gets a little trickier. So 2 pi thirds. So sine of 2 pi thirds is root 3 over 2. Right? Sine of 2 pi thirds is root 3 over 2, positive. And what's 1/2 times 2 pi thirds? Well, that's just pi thirds. Pi thirds plus root 3 over 2 without a calculator. Well, it's not that bad. I mean, pi thirds, that's about 1, right? Pi is 3.14, so 3 divided by 3 is about 1. And root 3 over 2 is 0.8 something. And you really should know that, to be honest with you. Root 3 over 2 is 0.866. 1/2, of course, is 0.5. Root 2 over 2 is 0.707. I mean, really, those are your main trig values. So you really should probably know those, or at least in the ballpark with those. So this is about 1 plus about 0.8 something. So I just call it 1.9. Probably close enough. Just because I just got to tell what's my biggest and what's my littlest, right? That's all I need. And then 4 pi thirds, you take half of that, well, that'd be 2 pi thirds. And then sine of 4 pi thirds, that's down here in this quadrant, so it'd be negative root 3 over 2. So this is 2 pi, which is about 6. 6 divided by 3 is about 2. So this is about 2 take away about 0.8. So it's about 1.2. Okay, well, clearly this one's the biggest, and this one's the littlest, which were my endpoints. Well, look what we said the graph of f did. It went up, and then it went down, and then it went up. Well, clearly, it didn't go up enough or go down enough, right? It started at 0. It went up to 1.9, which is that number. Then it went down to 1.2, and then went up to 3.14. So there's your max, there's your min, back at the endpoints, right? So that's kind of what the graph of f must look like, right there. Okay? So we got our max value, we got our min value. That's global max min. Okay, let's move on to calculator stuff. So Zach, you're going to be busy here. Now, everybody else ought to have their calculators ready to go here, because I told you you're going to have a no calculator. We've been kind of emphasizing the no calculator part of this. But today, I really want to make sure you can do the calculator part, because I guarantee you're going to have one like this. Now, I apologize for not really emphasizing to you that this is a calculator problem, but this 2x would really be an issue here. Trying to solve this without a calculator, you're just going to run into a mess, right? So this one, you would just be told right from the get-go that this is a calculator. Now, what was the interval? It said from 0 to 5. All right. So one of the things that I said was important was, Will asked me, should I just draw a graph? I rarely do the graph on my graphing calculator, right? Because I could do that, but that's not going to be part of the work I have to show. So I usually don't do it. We start these the same way. Now, what's the question asked? We should look. 44 says, are there any stationary points? Well, how do we find stationary points? Derivative, set it equal to 0. So we're going to do that in a minute. Where is f decreasing? Well, that's going to be our number line, right? Our number line is going to tell us that, the plus minus stuff. Max min values, well, that's going to be my list of candidates, right? Which is where the derivative is 0 or the endpoints, right? So I'll have that. I'll do list of candidates. And then where is f concave up? What do I need for that? Second derivative, set it equal to 0, do a number line on that. Okay, so this problem basically has all of it in it, right? If we go back to this review thing that I had right here, okay, if we go back to this, it's pretty much got all this. We're going to do a number line for f prime, we're going to do a number line for f double prime, it tells concavity, we're going to have to do a list of candidates over here, right? So we're going to have to do it all, but we're going to do it all with the calculator, okay? So we're going to write it out though. So I have to do f prime. So I would say, so let's do both, okay? What's the derivative here? Negative 2 sine x plus 2 cosine 2x, because I have to kick out that 2, right? Equals 0. We're not going to be able to solve that without a calculator because of the 2x in there and the x in there, and that's just going to be a mess. So we're going to go ahead and solve this on the calculator. Now, Zach and everybody else, if you want to let the calculator do the derivative for you, which I'm fine with, that's fine on this one, we can do that right by the 9. So go up to the 9, and the derivative, I think I've shown you this before, the derivative is right here. Okay? And then second derivative is right next to it, but we don't really need that probably. So, and then you put an x down there in the bottom, and then you type in your function. So what was it? What was the function? 2 cosine x plus sine 2x. Now you're going to have to type in the derivative because you're going to set it equal to 0 to solve anyway, so it's not a bad idea to do this, but it's totally up to you. Okay, and that's all you got to do, hit enter. Now notice how it wrote it different than I wrote it, right? Because it switched around because of the minus sign, it switched around, but I don't care. Now, it'd be nice, we already know by reading ahead, we're going to need the second derivative, right? On this one. Now, sometimes you won't. If the problem wouldn't have asked about concavity, we wouldn't need the second derivative. But I would say, let's go ahead and do the derivative again. So we have it up here. We can always go grab it when we need it. Okay, so let's just do, while we're at it, go to do the derivative again of that. So do derivative, there you go. And then put your x. Then arrow, now, see he's in that blank space right there? Right there now. He can arrow up and grab, because we want the derivative of the derivative, right? So he can grab that, hit enter. They'll paste it right in there for him instead of retyping it. It's up to you though. Hit enter, there's your second derivative. So then we now got our first derivative, we got our second derivative both on the screen. Now, what I need on my paper though, is I'm going to need, when I'm ready to do the second derivative, I'm going to need it. Now I could write it down right now, but I'm not good at it. Okay, so I got f prime equals 0. So now we need to solve this. Okay, so Zach can go to his calculator, or everybody can, and we're going to do a solve. Now we're going to do a solve. So you don't have to do the derivative, right? You should know the derivative rules, so you should be able to do the derivative without the calculator. But if you want to double check, fine. Okay, now we're going to do a solve. Okay, go find the solve, Zach. Where's the solve? You know where it is? Menu. Or you can just type the word solve. Down on algebra, solve. And you want to know where solve is. That's going to be your friend. There you go. Okay, and we want to do the derivative, so go get the derivative. No, don't, it's, yeah. There he did it. It's right up there. That's the second derivative. There you go. Do the derivative equals 0, comma, x. Everybody's got to be able to do this. On the quiz on Monday, if you can't run your calculator to do a solve, right, you're going to be throwing away about 7 points probably on a problem right there, okay? Got to be able to do this. And then you go outside the parentheses, and what do we put? Vertical bar, which we get underneath by the equal sign, control and the equal sign, which tells us with. We want to solve this with, but remember, we got to go, we put the comma x inside the parentheses, and we got to do the with outside. If you come up to me, and here's things I see all the time. People forget the comma x. People forget the equals 0. They just put the derivative. And they come up to me, they say, hey, my calculator's not working, I say, hey, it's a test. I'm sorry. Not going to help. You got to know how to run your calculator. You got to know how to run your calculator, okay, on this test. Okay, it's ACT, right? ACT, it's always going to help, right? If you're using your calculator. AP test, it's always going to help if you're using your calculator. Okay, with, and we want to be between 0 and 5. Where'd you get? Where'd I get the 0 and 5? I don't know. I just made it up, I guess. I looked at problem 45, I think is what I did. Thank you for catching that. I think I looked at the wrong problem. Okay, so we got to go 0 to pi. Okay, so what do we type next? Help him out, everybody. Somebody. Nope. 0 less than or equal to x less than or equal to pi. Way down, there you go. Got to be able to do that. Okay, got to be able to do that. Okay? Come up here and take a picture of the screen or something. I don't know. You got to be able to do it.
take a picture of your calculator, I don't know. Gotta be able to type that in. Okay, now, now this warning is gonna say, more solution means this for the problems we do, don't worry about, you don't have to worry about. Okay, so now, so let's write it down. Now, if I were doing it, because if we have to, plug these values in, we might need more than 3 decimal places. So if I were doing it, I would probably write down more than 3 right now. But it does ask for stationary points, so you really only need 3, but I might have to plug those in later, so I'm going to probably write like 5 or 6. So what do we got here? Read them to me, Zach. 0.5.
5, 2, 3, 5.
Give me 6 decimal places. 9, 8. Okay, give me the next one.
2.61799.
Is there any more? Scroll to the right. That's it. There's only 2 of them. Okay? All right. So good. There could be more than that, but whatever. Now you only really need. So that is one of the answers that they wanted. I think that's 44A. Is there any stationary points? Those are the stationary points right there. Right? So we'd only have to give them as 3, but okay, that is it. All right, then. Where is F decreasing? So now we need an F prime number line, right? So we're going to put those. Now here on your number line, I don't care how many you put, that doesn't matter. That's just for you here, okay? And so now we need to pick a number. Now, we're going to use our calculator, so it doesn't really matter what numbers we pick here. Just make sure they're numbers somewhere in between there. So I can do 0.5, I can do 1, I can do 3, right? Just something in between. Now, here's where, remember yesterday or the other day when I showed you the thing with the curly brackets and stuff like that, right? We are now going to plug these 3 numbers here into F prime. Now, there are a bunch of different ways to do it, and you have to do whatever you're comfortable with on the calculator. But go up and grab the F prime. Here's what I think is a good way to do it. Now, if I were doing it, I'd do the curly brackets. I could do all 3 at once, but I think people get confused by that sometimes. So he went up and grabbed his F prime. You got to know what you're trying to plug into, right? We're doing an F prime number line, so we're plugging into F prime here. So he grabbed F prime. What do we put next? What did I say to put here? Now I want to plug a 0.5 in. So one option would be to go in and put a 0.5 everywhere the X is, right? So one option would be to just go in and erase that X, put a 0.5, erase that X, put a 0.5. That'd be an option, right? Okay. Once you do, or we could do what I say. Remember what I said here? Do the vertical bar, right? So you can do the vertical bar. Now don't get confused, because some people do get confused with the vertical bar on the solve, right? I don't want you to get confused on that one. I want you to know how to do the solve. But the vertical bar just means with. So we're telling the calculator we want to do this with X equals 0.5. So that'd be a way to do it right now. Okay, so we can either put a 0.5 in for the X's, or we can do the vertical bar real quick here, Zach. So do the vertical bar, X equals 0.5. Now we said we could do a curly bracket. We could do 0.5, comma 1, comma 3, put them all in. But let's just do one at a time. So 0.5, so we get a positive. That's all we care about, right? It's positive. Okay, so now put in a 1. So that was positive. Now change that 0.5 to a 1. So he just went up and grabbed this. Now he's going to change it to a 1. And oops. So you get that, right? Well, what do you do when you see that? We have control in it. We want a decimal. We want to do approximate. So we control it. Just hit control enter. It'll redo the same thing you just did. Aha, it's negative. Okay? And then put in a 3. I'll bet it's going to be positive, right? I think it is, right? So then you just change it to a 3. Got to be able to do that. Got to be able to take that derivative, and you got to be able to plug in these numbers with your calculator. It's crazy that the calculator one should be harder than the no calculator one, but if you're not comfortable running your calculator, that's where you run into trouble. Okay? You could practice these all day long. Now, you wouldn't know if you were exactly right, but you could change this to a minus. You could put a 3 in front of that or something. That'd give you a whole new function to try and practice this on with your calculator. Okay? So, where is the function decreasing? Well, between 0.523 and, now here's where you'd have to give me 3 decimal places, right? You don't have to round them. You can use 617 or you can use 618. That's fine. You go 523 or you go 524. It wouldn't really matter, right? But where is it decreasing? So then you would say from 0.524, I guess, to 2.618. that would be where F is decreasing, right? F is decreasing in that interval. So if you were gonna actually answer 44B, that would be the answer. But just understand, I could ask a lot of different questions. Local max and min, is there a local max on this? Where's the local max? 0.523 is the local max. Now remember how you have to write that out? Because F prime is changing from positive to negative, so therefore F is changing from increasing to decreasing, right? If I ask you about, they didn't ask about local max here, but I might have, right? So you can do that, and there's a local min, right? And you got to write out that rationale like we've talked about, okay? All right. Then it says find the max and min values of F. Okay, that's your list of candidates. Okay, what do we check? We plug those into the original. We have to check the endpoints. So we have to plug in 0 and pi. And we have to plug in our, and this is where you'd want to plug in more than just 3 decimal places, 325, 598. And I'd want to plug in 2.617993. Right? And I want to plug, that's my stationary points and my endpoints. I need to plug in to which function? Which one? The original F function, because I want to find the max and min values of the F function. So if you want the values of the F function, you got to plug into the F function. So back to the calculator, and again, so he's already doing, is that the F function there? Oh, you did the 3. Okay, so now we got to get the original function, which I don't think you've typed in anywhere yet. So you probably just need to do it right now. So that'd be 2 cosine x plus sine 2x is the original function. And then he can do the vertical bar again, right? He can do the vertical bar. We can plug in all these numbers we want to plug in. 0 is so easy, we probably could just do it, but go ahead. Let's do 0. No, come on now. Just look up at the ones you just got to do. Look at this one. Look at this one. Look at the one you just did up here. There you go. Okay, so that's a 2. So we put that in there. And then we want to plug in a pi. Okay, and that was -2. So we're just doing this. So you see how my work looks exactly like it did when we were doing it no calculator. This all has to be there like this. Okay, now we're going to put 523, 598 in there. That's why I wrote down all 6 of those, because I want my final max value that I have to be correct. Yeah. It's kind of tough to be writing and doing this at the same time. So what was it? 2.59. Okay, so 3 decimal places, that's good enough. And then 2.617993. -2.598. Okay, some symmetry there, which shouldn't surprise us. So my minimum was here, and my maximum was that one. So my min and my max are right there. Now, see now, isn't this interesting? Because we just got done doing 37, which we said was positive, negative, positive, went up, and the max and mins were at the end point. Well, guess what this one did? This one also went up, but this one goes here, and it starts at 2, and then it goes up to 2.598, then it goes down to -2.598, and then back to -2 at the end. So here, it went up, but the difference was my max and min values were at my stationary points, right? My highest and lowest points were there, instead of, on this one, they were actually at the end points, instead of the stationary points. Okay, so that's what that told us there. All right, and then finally it says, where is f concave up? I'm going to leave the rest of that for you to finish, but what do you need? You need the second derivative, so you're going to need to get that. You can do that on your, well, we already had it on the calculator, but I want to give you some work time here. So he would go back up to his second derivative, set it equal to 0, do a solve with the vertical bar, 0 to pi. It's going to be a good one for you to work on here when I give you some work time to make sure you can run your calculator. So he's going to solve the second derivative, get those possible inflection points, okay? He's going to do you'll do a number line for that. You got that equals 0. You're going to find those values, da-da-da-da-da. You're going to do your f double prime number line, and then that's going to give you your concavity, tell you when it's concave up, okay? So you'll finish out the problem doing that. All right, so I really have nothing new, like I said, to talk about, so we spent a lot of time going over homework. So basically, you guys can get started on this, and so much like today, I've just got some problems to do out of the various sections. Okay, so you can get started on that. I can help you answer questions, whatever, but that's it. I mean, really, we just went, that's a pretty good quiz review right there. I mean, we did some max min, we did some derivative rule stuff, we did some max mins, we did global, we did with a calculator, we did without a calculator, we talked about concavity and inflection points and number lines, and we did differential equations where we did some verified, the T-chart verified that it was a solution.